Double derivative. Very good. If it again becomes 0, okay, let me tell you a simple trick. No need to go for double derivative. By using single derivative, you can know. Okay, for that, let me ask you some simple questions. Distinguish between minima and maxima. Okay, so let f of x equal to this one, x square minus 3x plus 2. Let me take a function. df by dx equal to 0 means I want to equate the derivative to 0. So whatever value I will get, that value may be a maxima or that value might be a minima, right? So df by dx equal to 0 means if I will get the differentiation of that function with respect to x, I will get 2x minus 3. So 2x minus 3 by equating it to 0, what I will get? X equal to 1.5. So now whether x equal to 1.5 means 1.5 is a minima or maxima. How will you know? By taking a nearer point to 1.5. Take a nearer point to 1.5. Let's say x equal to 1. Okay, put the value of x, f of 1. What you are getting? 0. So f of 1 equal to 0. Whereas f of 1.5 equal to minus 0.25. So you see, at 1.25 the derivative is 0. Okay, and at 1.25 the function gives you minus 0.25. Whereas to a nearer point f of 1 it gives you 0. So 0. Minus 0.25 is smaller than 0. It means what? It is not a maxima. Because if it is a maxima, it can't become a maxima, right? It means what? It is a minimum. All of you have understood? Yes? So again, why I am telling all these things? Because we are going through neural network and deep learning. And all these things are required to this. And the mathematics students, if they are thinking that they do not contribute to this world, I will tell you that you are wrong. Without you, we can't do anything. Right? So you see, how will you use your knowledge in developing a new optimization algorithm? Okay, a new optimization. So let me go through different error functions with different minima and maxima. Okay, so you see, it is a error function with a single minima but no maxima. This is a error function with a single maxima, no minima. This is a error function with no maxima and no minima, right? This is a error function with multiple minima and multiple maxima. And a neural network, the error function is usually like this, which contains multiple minimas and multiple maxima. So you see, solving a error function with one minima is difficult, or multiple minimas are difficult. Multiple minimas are difficult because you might stuck in a local minima, right? So if you see, out of all the minimas, all are local minimas except one. This is the global minima, right? So one is the global minima. I hope all of you understand English and you can easily distinguish between local minima and global, right? Next. So now, how will you use these things to train a neural network, right? So let me simplify it by going through a single neural model. Then we can scale it to a multi-layer neural network and even to deep neural network, right? So you see, let's take a cat neuron with n number of inputs. Each input is associated with some weights, and we are adding a bias component. Now all of you are clear that why we are adding a bias component. Now we will get the weighted summation of inputs. We will pass it through an activation function so that we can get the actual output. So now you see, in the step number 1, we have to define the loss function. So loss function means error function, right? Which is nothing but y minus y dash. So for all points, if I want to fit a straight line for computing the weight of a person based on the height. So you see, how many heights and weights I will measure. For each student, one height and one weight. Yes or no? That is my one input. Okay. Means for that particular height there is a corresponding weight. Yes or no? So here that's why I have taken I equal to 1 to n, means for n input instances I have computed the sum squared error. Right? You can also compute the mean squared error. Okay. Next, define the optimization problem. What we want to do? We want to minimize the error. Minimize the error means we have to minimize the y minus y dash whole square. Right? Summation of I equal to 1 to n. Now, y minus y dash means what? Y minus, what is y dash? F of W transpose X plus B. You see how I have got it? You see, VK, what is VK? W1 into X1 into W plus W2 into X2 plus Wn into Xn plus Bk. So I can represent it in terms of a dot product, that is W transpose X plus B. So next, this Vk, I am passing it through an activation function f of Vk to compute the output. So what I will do, I can make this one into f of W transpose X plus B. So let me go to the optimization problem. We have to minimize the loss. Loss means y minus y dash. Y minus y dash means y minus f of W transpose X plus B with respect to the weights and biases. So minimize the loss with respect to the weights. So if I will consider the bias as also an additional weight, so I can write it as minimize the loss with respect to the weight. Okay. So here I have used the terminology regularization. With time to permit, I will tell you what is regularization and what are the types of regularization and why it is needed in unit. Next, we will go to the step number 3. So you see 3 steps. First step, define the loss function. Second step, define the optimization problem. Third step is solve the optimization problem. Okay. So how will you solve the optimization problem? So all of you have heard a term gradient descent. Okay. In gradient descent, what we do? We first randomly initialize the variables, or here what we will do, randomly initialize the weights. Because what do we want to do? We want to minimize the loss with respect to the weights. So what we can change? Input we can't change. The activation function we can't change, but the weights we can change. So we will randomly initialize the weights. Then what we will do? Feed forward the inputs and compute the loss. So you see that these weights I have randomly initialized, right? Next, input we know, because if in your case, what is the input height and weight? Height is the input, you know the input. So that height you can multiply with the randomly initialized weight, yes or no? So this input multiplied with the weight, then we will get the sum of weighted summation of inputs. We will get the bias. Then we will pass it through an activation function. Then we can compute the y dash output. Then we can get the loss y minus y dash. Y means actual height, actual weight, and y dash means computed weight. Right? So step number 2. What is the step number 2? Feed forward the inputs. Feed forward the inputs means W transpose X plus B, and we will pass it through an activation function F. Right? So that we can compute the output. So y minus y dash, you can take the square, so that you can compute the loss function. Is that clear? Yes. Then what I will do? We have to update the weights. So this is the important thing. What you will do? You will update the weights. Again, you will get the new weights. Then you will again feed forward the inputs. You will compute the output. You will compute the loss, right? And you have to update the weights in such a manner that the loss should minimize. Means in the previous iteration, if the loss is 5.0, in the next iteration it should reduce. It should not be more than 5.0. It can remain same, but it can't increase. Right? It should not increase. So how will you guarantee that it will not increase? You will compute the derivative of the weights. Yes or no? Because derivative will give you the direction in which direction you will update the weights. Yes or no? So now you see, so we will update the weights. So which weight we will update? We will update W1, we will update W2, we will update W3, WN. Okay. So W weight, we have to minimize what? We have to minimize the loss function with respect to the weight. So we have to take the partial derivative of loss with respect to each weight. So we have to compute dou L by dou W1, dou L by dou W2, dou L by dou WN. Okay. So let me compute dou L by dou W1. So dou L by dou W1, you see, dou L is the loss. So while computing the loss, you are not taking the weighted summation of inputs only. You are passing it through an activation function. So if you know the chain rule of derivative, I can represent it dou L by dou W1 is nothing but dou L by dou F into dou F by dou W1. So now you see dou L by dou W into dou F by dou W1. So let me compute it. Okay. So you see dou L by dou F. Dou L by dou F. Dou L. L means what? Sir, F of W transpose X plus B. Yes. Whole square. Yes. Y minus F of W transpose X plus B whole square. Right? So that is the toss. You see over here. L is y minus y dash whole square. Y dash is what? F of bk. Bk is W transpose X plus bk. So you see f y minus y dash whole square. So if I will take the derivative over there, so square term will become what? I will get it to over here. But you see y minus y dash, and the f comes over where? F comes in y dash. Y dash means what? F of W transpose X plus bias. Are yes or no? So you see the f is in negative term. That's why I am getting minus 2. Is that clear? Next, f is applied on what? F is applied on y dash. Right? So I am getting minus 2 into y minus y dash. Next, dou f by dou w, what you will get? Dou f by dou w. F is applied on what? F of W transpose X plus B. So dou f by dou W. What you will get? W transpose X plus B. So B will be a constant, it will be removed. W transpose X. Dou by dou W of W transpose X means you will get X. Okay? So you see, so if you will use simple derivative rules, you can get it. Right? So I have got what? Minus 2 into y minus y dash into X. So this is the value of dou L by dou W1. Similarly, I can get the value, all the values. Right? Now the important thing is you have to update the weights. So how will you update the weights? All of you please listen carefully. If you haven't understood the derivative also not an issue, you can go through it. Okay? But how will you update the weights? Wi new. So W is a weight vector, right? W new equal to W old minus nita into dou L by dou W. Dou L by dou W is the derivative, partial derivative of loss with respect to that particular weight. And here, why I am adding a term nita? Nita is called as learning rate. Means the rate at which you will update the weights. Means whatever partial derivative of loss you are getting, you are not updating by that. You are taking a fraction of that. So nita might be a value between 0 to 1. Are you getting a little bit? Yes or no? Otherwise, you see, your time is very, very important. If you are not getting, you please tell me, sir, I have not. If you will not understand this, you can't understand the further steps. Right? All of you have understood up to this? Okay. So now you see, now we will go through. So here I have used a neuron. The same concept can be extended to any number of layers and any number of neurons. So let me go through the types of neural network. So one is single layer neural network. Single layer neural network means one layer is input layer and there is a neuron which is the output layer. Means one layer of neuron and one layer of input. And another type is multi-layer neural network. Means one is input layer, one is output layer containing a neuron, and in between that, any number of layers you can keep. And you see, in any layer, you can keep any number of neurons. Now the question is, sir, how to know how many number of layers and how many number of neurons in each layer? Is that clear? We will go through it at the end. Okay, how to optimize the hyperparameters of a deep neural network. Next question is, instead of single layer neural network, the multi-layer neural networks are very popular. So the question is why? So first thing is biological inspiration, because we are motivated by our human brain or biological nervous system, which consists of millions of neurons with trillions of interconnections. So that is the major motivation to go for multi-layer neural network. Next one is universal approximators, means can approximate any nonlinear function to any desired level of accuracy, right? So the function, so you see the output is a function of the input. So that function may be complicated, right? But how much complicated it can be, not a problem. A multi-layer neural network can approximate any nonlinear function to any desired level of accuracy, provided that you get the right weights, right biases, right activation function. Is that clear? Okay. And the next important thing is results in powerful models. So you see, if you will in Google, if you will plot this function, okay, 2 into sine x square plus sqrt x into 5 or 5x. So you see, this is a complicated function. But now you see, I can represent this by using a neural network. You see how will I represent? So you see, x and 5. I will use a multiplicative unit. So what I will get? 5x. Okay, this one. Right? Next, I can use a sqrt function to the output of 5x. So what I will get? sqrt of 5x. Similarly, x, I can use a activation function square, right? So that I can get x square. Then I can use an activation function sine, so that what I can get? Sine x square. Next, sine x square multiplied by 2, I will get 2 sine x square. Then 2 sine x square plus sqrt of 5x. I can use a additive unit over here, so that you can get the complicated function. Similarly, you can approximate any nonlinear function to any desired level of accuracy, provided that you choose the hyperparameters appropriately. Yes. Next one is another type of neural network, sir. One is feed-forward neural network. Another one is recurrent neural network. So in feed-forward neural network, the input flows towards the output, whereas in recurrent neural network, it is a directed cyclic graph, where the output of one layer may be given as input to the previous layer, right? So next one is backpropagation algorithm. So this one I have already told you. What is that? First you have the sample label data. Then you have to randomly initialize the weights. Then you have to feed forward the inputs to get the outputs. Then you have to backpropagate the errors. Then you have to update the weights. After updating the weights, again you have to feed forward the inputs. Again compute the error. Again compute the derivative of the error. Again update the weights. But now here one important thing is how or when do you update the weights? Based on that, there are three types of gradient descent. One is stochastic gradient descent, another one is mini-Wells gradient descent, and another one is gradient descent. In stochastic gradient descent, what you will do? You take one input, okay? You feed forward it, compute the error. Then based on that error, compute the gradient of the error. Then update the weights. Then again take the next input, feed forward it, compute the error, take the gradient of the error, update the weights. Right? Means for each input, there will be weight updation. Whereas in gradient descent, what you will do? You take the the inputs one by one. One input you take, compute the error, but don't update the weights. Take another input, compute the error, feed forward it, compute the error. Then take another input, feed forward it, compute the error. Then after taking all the inputs one by one, feed forwarding it one by one, computing the error one by one, compute the mean square error, then update the weights. So the intermediate of stochastic gradient descent and gradient descent is the mini-based gradient descent. Where what you will do, instead of updating the weights after each input, or instead of updating the weights after all the inputs, you will do updation of weights after a base of inputs. Means let's say you are having 100 inputs. Okay. So you will take the base size is 10. Means after feed forwarding 10 inputs, computing the error of 10 inputs, computing the sum of errors of 10 inputs, you will update the weights. Is that clear? But here the important thing is what should be the base size? That is again one hyperparameter. So how will you optimize it? That we will see. Right? Next. So next we have gone through the basics of neural network. Let us get into deep learning. But why I have gone through the basics of neural network? Because deep learning is an extension of that. If you don't know that, you can't understand this, right? So you see, actually, this diagram I have taken from the famous book Deep Learning with Python by Francis Chollet, who is the chief data scientist at Google, right? So you see what he has told. Artificial intelligence is the superset of machine learning, and you see the machine learning is the superset of deep learning. And artificial intelligence has begun from 1950s, and by the time we got up to 1980s, we have coined a new term machine learning, and by the time 2010, we have coined a new term deep learning based on a special type of machine learning model, that is neural network. Now, the question is, before going through deep learning, let me go through the formal definition of deep learning. A type of machine learning based on artificial neural networks in which multiple layers of processing are used. So, deep learning is based on what? Neural networks, right? Which is a type of machine learning. And in which what we will do? We will do multiple layers of processing. So you see the number of layers. If there are thousands of hidden layers, so what we will do? The same thing. Input, multiply with the weights, transfer it through an activation function, get the output of a particular layer. Then the output of that layer will be served as the input to the next layer. Again, what you will do? You will multiply the outputs of that layer to the weights, transfer it through an activation function, and that will be the output of the next layer. And this process goes on, right? So here we are not doing anything else rather than we are doing a element-wise processing in a layer-wise basis. Okay? Why we are doing it? So that we can extract progressively higher level of features from the data, right? So how you will get that we will go through. Okay? So now, basically there are two kinds of approaches. So here two kinds of students are also sitting. One is mathematics students, another one is our engineering students, right? So mathematical approach. What is that approach? First build new theories, okay? Then after building the theory, to perform experiment on that. Whereas in deep learning or the engineer's way, what we will do, first perform experiments, okay? Given the huge amount of computational power nowadays we have, we first perform experiments. Then from those experiments, we try to derive the theory, right? And in deep learning, what I will tell you after this slide onwards, all are following the engineer's way. Means first they perform the experiments, then from the experiments they try to derive the theories. So, but before going through that, let me tell you why deep learning, and the biggest question is why after 2010, not before, right? Okay. So you see, Computer vision. So in computer vision, we are using convolutional neural networks, but that is well understood since 1989. But sir, why it has become popular after 2010? Why not during 1989? What was the problem? Time series forecasting, your speech recognition, all those things what you are doing. Long short-term memory that is widely used, that is well understood since 1997. But why not then and why now? The answer to this question is there are three things. One is due to the boom of internet, there is lots of data. Okay. And second one is algorithmic advancements that have taken place which popularized the deep learning models. And the third one is hardware advancements. So you see the deep learning models require high computational overhead. And due to the advent of GPU, graphics processing unit, now it is possible to do such kind of large experiments. But now here you see, I can't explain you the data that you know. I can't go through the hardware advancements, but what I can go through, I can go through the algorithmic advancements that make deep learning popular, right? After 2010, right? So what are the algorithmic advancements? So the first one is better activation functions for neural network. So I hope now all of you know what is an activation function. If not in detail, but still have some idea, right? So there are some better activation functions that have been developed after 2010 that make it possible that deep learning becomes practical. Next one is better weight initialization schemes. So you see, in neural network, in order to obtain the near optimal weights, what we are doing? Initially, we are randomly initializing the weights. Okay. So if you are fortunate enough, if your initial weight selection is from a good location, then you may get to the near optimal solution. But if it starts from a local optimum, you will track to the local optimum. But after 2010, they have developed some weight initialization schemes that makes it helpful so that the deep learning models become popular. Another one is overfitting concepts. To avoid overfitting, concepts like dropout is introduced and better optimization schemes. We will go through the optimization schemes that have been developed recently. Okay. So first one, let us go through activation function. So what is an activation function? I have already told you if a mosquito bites you, you don't bite the mosquito. You kill the mosquito by other hand. Means whatever weighted summation of inputs you are getting, you are giving in response to that. And in order to give the output response to the net weighted summation of inputs, you have to use an activation function. And the next thing is our data, the real world data is highly nonlinear. So in order to handle nonlinearity, we have to use nonlinear activation functions. Okay, so activation functions also help in handling nonlinearity that the network can learn complex patterns. Okay, so what was there previously before 2010 and what had changed after 2010? So let me go through that. So first one is before 2010. Nowadays also, sigmoid activation function is widely used. So sigmoid activation function, what is the formula? F of x equal to 1 by 1 plus e to the power minus x. So what is the advantage? One is differentiable. So you know that if it is not differentiable, you can't get the derivative of the loss, you can't update the weights. So first thing is it is differentiable. Second one is it is nonlinear. So it can handle nonlinear patterns. Right? Third one is output lies between 0 to 1, which makes it possible for hardware implementation. Third one is fast. Why fast? Because you see, you will find the derivative of sigmoid activation function. It can be represented by itself. F dash x equal to sigmoid of x into 1 minus sigmoid of x. It means its derivative can be represented by itself. Okay. So you see, in gradient descent, what you will do? Feed forward the waves, compute the error, compute the loss, compute the gradient of the loss, then you have to update the weights, right? So So while computing the gradient of the loss, if the derivative of activation function is easy, then it will take less computational burden, or then it will take less computational overhead, right? But there is a big problem in sigmoid activation function, that due to that the deep learning models hasn't become popular before 2010. What is that problem? That is called as vanishing gradient problem. So what is vanishing gradient problem? So you see here the important thing is the output lies between 0 to. So in a larger or deeper neural network, let's say it has 100 number of layers, right? So if it has 100 number of layers, in order to update the weights of the first few layers, what do you have to do? Dou L by dou F1, dou F1 by dou F2, dou F2 into dou F3, because every layer has an activation function. Yes or no? And in order to compute the gradient of loss, you have to use the chain rule, and you have to compute the loss, right? But now you see the derivative of sigmoid is what? So sigmoid of x into 1 minus sigmoid of x. Sigmoid of x lies between 0 to 1. 1 minus sigmoid of x will lie between 0 to 1. 0 to 1 multiplied with a 0 to 1. It will be much smaller. Yes or no? Now you see dou f by dou L. Dou L by dou f is a small value. And in a deeper neural network, we will have what? Dou L by dou f, dou f1, dou f1 by dou f2, dou f2 by dou f3, dou f3 by dou f4, all the activation functions of all the levels. So the gradient term will become very small. So if the gradient term becomes very small, how we will update the weights? W nu equal to W volt minus beta into dou L by dou F. Yes. So if the gradient term becomes too small, W nu will become W old. It means there will not be any weight updation. Yes or no? So if there will not be any weight updation, then the error will not get reduced. Is that clear? So that is the problem. That's why the name is vanishing gradient. Means the gradient will become 0. Right? So in order to avoid this problem, you see, this one what I have explained right now. Okay? So after 2010, an activation function is developed that is called as ReLU. Right? So in ReLU, f of x equal to x if x is greater than 0, and f of x equal to 0 if x is less than. So here you see the output doesn't lie between 0 to 1. Is that clear? And the gradient you see, f dash x equal to 1 for x is greater than 0, and f dash x equal to 0 for x is less than 0. Yes or no? So what is the problem? If the gradient becomes negative, then dou L by dou F becomes 0. So if for negative value gradients, the weight updation will become 0, then what is the problem? You might get dead ReLU units. Dead ReLU units means for those units the weights will not update. So what is the solution? So an engineer like you or a mathematician like you thought that, sir, why to make the gradient 0 if the value is less than 0? What we will do? We can take a fraction of the input, right? And they have developed literally. So you see in literally what they have done? F of x equal to x when x is greater than 0. And f of x equal to 0.1 into x. 0.1 you can change, 0.2 into x, 0.15 into x, a fraction of x, right? If x is less than 0. So it avoids the problem of dead ReLU. So due to development of these kind of activation functions, the vanishing gradient problem has been avoided. So if vanishing gradient problem has been avoided, then what we can do? We can train deeper neural networks, right, with any number of layers, right? So this is one thing that has made the deep learning or deep neural network popular after 2010. And the next thing is weight initialization. Okay, so some new weight initialization schemes has been developed which made deep neural network popular after 2010. We will go through some of them. Okay, so now you see how weight initialization will affect the training of deep neural networks. So you see, here you see, let me go through an error function. This is the error function. So you see this error is a function of what? Weights and biases, right? So here bias, let me consider it also a weight, right? So now you are unfortunate enough. So you will initialize the weights randomly from a poor location. Let's say you have initialized from that location. So after that, what you will do? Sir, feed forward the inputs, compute the output, compute the loss, compute the gradient of loss, then update the weights. But you see, if you will update the weights, your error will decrease. So you see, the error will decrease and the weights will be updated. But you see, it will stuck to this local optima. Yes or no? Because this is a local optima. But if you are fortunate enough, and if your initial weight is from this location, okay, then what you will do? You may go to the global minimum. Is that clear? So now have you understood the importance of weight initialization? If your initial weights are generated from a better location, then your learning will be good. Okay. So now, how they have done it? So they have followed engineers' way. They have first conducted experiments. Yes or no? So what they have done? They have developed the methods based on fan in and fan out. So what is fan in and what is fan out? Fan is nothing but number of inputs that is incoming to a neuron. That is fan in. Here what is fan in? What is the fan in for this neuron? 3. What is the fan out for this neuron? 1. Okay. So fan in is the number of inputs to a particular neuron. Fan out is the number of outputs that is going out of that neuron. Is that clear? So based on this, they have developed some formula to initialize the weights, right? So Xavier and Glorot first developed a weight initialization scheme. The first version is Wij. Wij means weight between ith neuron to jth neuron of next layer. Will be generated from a normal distribution with mean 0 and standard deviation sigma ij. And sigma ij is what? Sigma ij is nothing but 2 by fan in plus fan out. Right? Similarly, they have developed a method for second variation from the uniform distribution by using this formula. Is that clear? But there is no mathematical proof. How they have derived it? By conducting large experiments. Okay, we also do those things nowadays. We conduct experiments, and from that we try to derive that yes, it is giving better result. What might be the reason? Okay. Next one is, and most importantly, it works well for sigmoid activation function. The next kind of weight initialization scheme that has been developed in 2015, which works well for ReLU activation function, and the formula is this. You can go to the formula. I will send you the slides. Okay. So don't, I think I should not waste time on this. You can go through the formulas, right? Next one is bias variance trade-off. So you see, if number of layers increases, then what will happen? More number of weights. Yes or no? Number of layers increases means there are more number of neurons. More number of neurons means interconnection among the neurons are the weights. More number of weights. So if more number of weights, then the chances to overfit is high. So how? Let me explain this one by help of one example. Okay. So you see, I have a doctor. Okay. I teach her A. Okay. So what I have taught her, this is A. I have written one A. I have taught her. This is A. Then I have again taught her. This is A. So you see, after some time, she is able to recognize what is A. But I am a teacher. What I will do? No, no. I will make her expert in learning A. I have taught her A again and again, again and again. Then what she has done? She has tried to remember the angles. Okay. If the angle between this line and this line is 30 degree, if the angle between this arrow, this line is 120 degree and angle between this side is 120 degree, then that is A. So you see what she has done? She has remembered more features. Yes or no? Whether that is good or bad? Not always good. Okay. So next time when I will give an A to her, she will tell that, Papa, this is not A because the angle is not 30 degree. Yes. So you see, you also came across such situation. When you will practice, when a cricket player practices, sir, call match है, I will practice for 24 hours. Can he perform well in the match? No. कल एग्जाम है सर आज मैं रात नहीं सोऊंगा पढ़ते रहूंगा. Can you perform well in the exam? No, because of overfitting, right? If you tend to memorize the noise patterns while learning the things, then it will affect in generalizing the future patterns. Is that clear? So, if more number of weights, so what you can do? Sir, why you are taking 100 layers? I will take 2000 layers. It will give better result. No, that is not the case. By merely increasing the layers and number of neurons in each layer may result in overfitting. And overfitting means in training it will give you good result, but in testing it will give you poor result. And what we require? We require a model that gives better result in testing. Okay? Because in known scenarios, we know the input and target, right? Suppose I want to predict whether tomorrow it's going to be rain or not. For that, what I have done, I have used the train data, last 100 days data, and I am telling that yes, my model gives 100% result. But if it performs poorly on the test data, that is, if tomorrow it will say it will rain, but it will not, right? Then it's a problem. But if my model provides train error, sir, 50% it is correct, but in test data it works well, then that is a better model. Is that clear? So, the problem with deep neural networks is what? It tends to overfit. That is the problem of high layers. So, you might think that, sir, by taking large number of layers, it can overfit. So, we can take small number of layers. Yes. So, if you will take small number of layers, there will be number of layers decreases, less number of weights. Less number of weights means chances of underfit is more. If I will teach my daughter only one time A, ज़्यादा पढ़ाऊंगा तो overfit हो जाएगा. Yes, I will teach her only one time. This is A. Have you remembered? Then I will test on it. Then she can't perform because she hasn't learned the underlying patterns. Is that clear? And in order to learn the patterns, what do you require? You require variables, right? This line is like this line is like this line is like this. Then it is A. This is normal learning. But if you will learn the angle between the lines, that is overfitting. But if you will not learn perfectly, then N also, she can say that, Papa, this is not N, this is A. Yes, because she hasn't learned perfectly, right? So that is under learning or underfitting, right? So, what is the thing? So, by taking less number of layers, it is a problem. By taking large number of layers, it is a problem. So, for which problem, how many layers? For which problem, how many number of neurons in each layer? That is the big problem to answer. Yes. And if time permits, today I will tell you how you deal with that. Okay. So, in order to overcome this overfitting, in deep neural network, what is the problem? Chances to overfit is high, right? So, we want to avoid it. So, in order to avoid it, they have developed a concept that is called as regularization or dropout. Dropout and regularization. So, I will go through dropout. Okay. So, in deep neural network, we tend to overfit because of many number of layers and many number of weights. So what they have thought that if we will drop a certain percentage of neurons, then you see, if I will drop this neuron, okay, which weights will be dropped? These three weights will be dropped. These two weights will be dropped. Yes or no? So number of parameters are dropping or not? So I will not memorize many number of parameters. So why the overfitting occurs? Due to large number of weights. So, but if I will use a dropout rate, I will drop some percentage of neurons, then I will reduce the number of weights. Yes or no? So now the question is, how to set the dropout rate? If it is too high, underfitting, many number of neurons will be dropped. If it is too low, overfitting, few number of neurons will be dropped, few number of weights will be dropped. So how to get the optimal value of dropout rate? That we will see. Okay. But this concept has been developed, and due to that, the overfitting can be avoided. Right? Okay, you can go through this. Next one is Bayes normalization. What is normalization? Normalization is a pre-processing technique that is used to transform the features from one range to another range. So why it is required? You see, suppose I want to classify a person whether he is male or female. Okay. So one feature, let me take it as height. Okay. So what is my height? Let's say 170 centimeter, right? So one feature, the height feature will become what? Sir, 120 to 190. The values will be. Yes or no? Suppose let me take another feature, hair length. Okay. So you see in India, hair length of boys are shorter than the guys. Yes or no? So that might be also a better feature. But you see the hair length range should be what? Sir, 7 centimeter to 30 centimeter. Yes or no? Now, if I will give these inputs to a neural network, so you see one input range is 120 to 190. One input range is 5 to 30. So you see, for a smaller weight value for input 1, it will have a larger impact. Whereas for a larger weight value for input 2, it will have smaller impact. Yes or no? So in order to avoid these impacts of variation in range in the pictures, what do? We normalize the thing. Means for that column, we will map it between 0 to 1. For the second column, we will map it between 0 to 1. So what will happen? The first picture and second picture both will have same impedance. And you see, while normalizing, the important thing is we are not distorting its shape. Means if the height of SAR is 180 cm, I will normalize between 0 to 1. If my height is 170 cm, I will normalize it between 0 to 1. So after normalizing also, his normalized value is greater than my normalized value. Yes or no? So I am not distorting the shape. Although I am changing the range, but I am not distorting the shape. Right? So this is the major motivation of normalization. And there are various types of normalization schemes you can go through. Min max, decimal scanning, vector, z-score, all those things. Right? But now what is Bayes normalization and why it is important? So you see, in deep neural network, you will have many number of layers. So many number of layers means what you are doing? Sir, we are multiplying the input x to the weight w. W transpose x plus bias. So here we are getting a different input. Yes or no? Here this input will be multiplied with the weight sets added with the biases. So here in this layer we will get a different input. In this layer, much different input than this one. After few layers, the input shape may be lost. Yes, means what is the actual input shape that might be lost after few layers because of this element wise multiplication with the weights, transferring it through some activation function. So what we will do? Okay. So after few layers, we will use a batch normalization layer. That will do what? Although the features are transferred to a different feature, but it will keep that input same. Are you getting? Or it will keep the covariate of the input patterns. You see, it will avoid internal covariate shift. So those who are aware of covariate, I think the mathematics students are aware of covariate. Okay. So what they will do after multiplying or transferring the inputs from one domain to another domain repeatedly, the covariate may shift. So what we will do by following these equations, we will again map into the original covariate. Right? Next one is optimizers. So you see what we have gone through. We have gone through the activation functions. New activation functions after 2010, which was vanishing gradient. Next, we have gone through dropout and regularization. We have gone through batch normalization. We have gone through better weight initialization schemes. Next, the important thing is the optimizers. Means how you will update the weights. Right? Sir, suppose our weight initialization is perfect, but our updation of weights, initialized weights is not perfect. Then we might not get to the requirement. So how will we update the weights? So optimizers are the algorithms by using which what we can do, we will try to reach to a corresponding minimum. Right? So now you see at minima, maxima and saddle point, you have the gradient as 0. So up to when you will update the weights? When the gradient becomes 0. Yes, but in real life that will never come. Okay, the gradient will never become 0. You will always get a near optimal solution. So for some iterations you will go through, or you can set the termination criteria, rate of change of best solution. Okay, so like this you can choose. Okay, but the ideal case is when the gradient becomes 0, you have to turn. Right. So now you see the error function. This is the settle point. So here you see I have told you one thing, new thing. At minima, maxima and settle point. So minima, maxima, all of you are aware. I have already told you. But settle point is what? All of you have seen a horse. Yes. All of you have sat on a horse. You might not have sat, but you have seen it. You see, from one side it is minima, and where you are putting your legs, from the other side it is maximum. Right? Means a same point can behave as a minima from one side, one direction, and it will behave as a maxima from other direction. So you see, your optimization algorithm or your optimizer should avoid the settle points. Okay? Next. So you see, the error functions may be convex or non-convex. Convex means what? You can draw a linear line between any 2 points of the error function without going beyond the error function. But here you see, if I will take a point from here to here, by drawing a single line, I can't join. Right? I have to use a chord. Right? And such kind of error functions are called as non-convex. And in neural network or in deep neural network, the error function is a non-convex one. Whereas in support vector machine, the error function is a convex one, and you will always get the same result even you will run the algorithm for 100 times. But in neural network, sir, I have written a program in neural network, I have run it once. It has given an error of 2.5. But if I will run it again, it has given an error of 2.3. Can anybody tell me why the difference in error if you will repeat the same things? You have written the same program. Execute once, it will give you error 2.5. But you have executed again, it will give you 2.3 error. Why? Can anybody? Because the initial weights are selected randomly. Yes or no? The initial neural network weights are selected randomly. So you will always start from a random location. So if you will start from a random location, you will track to the corresponding optimum. Yes. And if you are fortunate enough, if you are starting from the same location, then you might get to the same solution. So don't get confused if you will get different results by running the same program different times. Okay. So stochastic gradient descent I have told you, gradient descent told you, Panigrahi told you. Next one is, let me go through the optimals. Because of lack of time, I am skipping some things. So now you see the rate of convergence of stochastic gradient descent can be improved by adding a momentum to the gradient expression. So what is gradient expression we have used? Sir, W nu equal to W cold minus meta into dou L by dou W. Right? Meta is the learning rate. Now, momentum means what? Momentum means we will add a fraction of previous weight change. Means you see how we are changing the weights. Sir, W equal to W old plus meta into dou L by dou W. Next, if I will change, I will become I plus 1. Then, if we have to do W old plus meta into dou L by dou W. Okay? But you see, while doing so, if we will add a momentum term, you see, WIT, T iteration to WIT, T minus 1 minus meta into dou L by dou W we have. The same thing as this expression. But here you see what we have done. We have added one another term momentum, alpha into del W T minus 1. Del W T minus 1 means what? The change of weight in the previous iteration. Means in the previous iteration, how much we have changed? In the next iteration, we will add a fraction of that. Is that clear? Yes or silence? Yes or silence? Silence. Okay. So now you see, next, this can be improved by using another Nestrov accelerated gradient. So you will see how the deep learning engineers and researchers are publishing papers by merely changing a thing. Okay, you just see. So you see, if in stochastic gradient descent with momentum, what we have Wi t equal to or Wi nu equal to Wi old minus meta into dou L by dou W minus alpha into del W t minus 1. Okay, we have this much. But in Nestrov accelerator, what we will have you see. So you see, this is stochastic gradient descent with momentum. So you see, we are adding a momentum term, we are adding a gradient term. It means if you know the law of parallelogram of vectors, right? So we are actually going in this direction. But you see, in Nestrov accelerator gradient descent, what they have done, what different things they have done. So you see, first they will add the momentum, then they will add the gradient. Okay. So you see, previously what they are doing, they are directly adding the momentum and the gradient. Okay. All of you please listen carefully to me. I will ask one mathematics student to explain this one why this is different. Okay. Previously what they have done, you see, they have parallelly added the momentum and gradient. This is dou L by dou W is the gradient term. Alpha into del W t minus 1 is the momentum term. Okay, they parallelly added it. Okay, but now you see, they have first in Nestrov accelerated gradient descent, they have first added the momentum. Then after that, they have added the gradient. So what is the difference? Can anybody tell me? Or whether is there any difference or not? You see, I am telling you x plus 5 plus 2. Okay. Then I am telling you, no, you will not do like that. You will do first x plus 5. Then you will do x plus 2 or new x plus 2. Then what is the difference between these two? You might think that there is no difference. But I will explain you in vector, there is a difference. For that, let me go through this diagram. So you see, This is momentum based gradient descent. Means you have momentum and gradient. But this is accelerated gradient descent. So I have told you what in momentum based gradient descent you will add momentum and gradient parallelly. Okay, at a time. Whereas in accelerated gradient descent, first you will add the momentum term, then you will add the gradient term. Then what is the difference between these? So you see here in momentum based gradient descent, let's say you have started from one location. Okay, you will update the weights, you will compute the momentum and gradient, you have added it. So it has decreased, third step, fourth step it will overshoot, then it will come to here, fifth step, then it will come to here, sixth step. Okay, suppose this is the case. The same addition I am doing it over here. So you see first step. First I have added the momentum, then I have added the gradient. So it has gone to that step. Then in the second step, no problem. First I have added momentum, then I have gradient. In the third step, no problem. But come to the fourth step. In the fourth step, here what I will add? First I will add the momentum. All of you please listen carefully so that you can easily understand. First we will add the momentum. It means what? It is a smaller term than momentum plus gradient. Yes or no? So here I am making a larger jump. Then here I am making a smaller jump. Right? So you see, first I have added the momentum term. Then I will compute the gradient. So here what is the gradient direction? In this direction. Yes or no? So you see, here after third step, momentum plus gradient. So it is jumping to this location. But here, first I will add the momentum, it will come to here. Then I will compute the gradient. Gradient always show you the direction in which you will reach the minimum, right? So here it will show you in this direction, not in this direction. Is that clear? So in accelerated gradient, you see what they have done. Instead of adding momentum and gradient at a time, they are first adding the momentum, then computing the gradient, then they are adding the gradient. Is that clear? So accelerated gradient is faster than your stochastic gradient with momentum. Have they done a really new thing? No. But they have published in a Tier 1 conference. Right? So next one is adapted. So here you see in accelerated gradient descent, SGD and SGD plus momentum, the learning rate is same for each weight. But in ADAGRAD means adaptive gradient algorithm, what they have done, they have set different learning rate for different weights. Why? Because of features. So you see, in real life, the features may be sparse or may be dense. For example, salary feature. It is a sparse feature, basic salary. It is a sparse feature or a dense feature. All the employees will have a basic salary, yes or no? But come to commission. Commission is a sparse feature or dense feature? Sparse feature. Because not all the employees will get commission. Only few employees will get commission. So now you see, we are setting learning rate that is same for all the features. That is not appropriate because the sparse features should have less learning rate than the dense features. Right? So that's why in adaptive gradient what they have done, they have set different learning rate for different features or for different weights. Right? And how they are updating the learning rates, I will tell you. So you see, they are taking neta t equal to, means at t iteration they are taking neta t equal to neta by root over alpha t minus alpha t minus 1 plus epsilon. Means where neta is the learning rate of previous iteration and they are dividing it by a factor. It means what? I will complete the optimizer. Okay. So now you see, knitted is the previous iteration learning rate, or this iteration learning rate. This is same to what? The previous iteration learning rate divided by a value, divided by a factor, right? So now you see, if I will divide it by a factor, then what will happen? The learning rate will decrease. Okay. Previously, let's say the learning rate is 0.3. Now it will become as what? 0.2. Then 0.1. Then 0.01. Then 0.001, like this. So why it is required? Okay. Why it is required? You see, here you see, first you see we have larger learning rate, then we have smaller learning rate, so that we can track to the local optima, right? But if we will fix the learning rate, then you see what will happen. The same learning will happen, and we might have a oscillation, right? But you see, in this case, if the learning rate will decrease, then what will happen? You see, it is the same one. It is the same one, the same by same factor we are updating. So here you see it comes from here to here because we are adding a fractional value to the old weight, right? It will come to here, come to here. It will oscillate. But if we will reduce the learning rate, then what will happen? Sir, initially it will change quickly, then it will change slowly. Yes or no? So what will happen? We will make a faster change of weights at the beginning, then we will gradually change the weights so that it will make a more local source around the optima. Is that clear? But what is the problem in this? Sir, as the number of iterations will increase, the denominator will increase. Yes, because see here I haven't told you one thing. The denominator is nothing but alpha t minus 1 is nothing but it is the summation of gradients of all the previous iterations. Means gradient of first iteration, second iteration, third iteration, fourth iteration. Next, for sixth iteration, it will be the summation of first, second, third, fourth, fifth. For the 100th iteration, it will be the summation of 1 to 99. So it will always increase or not? If it will always increase, the learning rate will always decrease or not? Yes. But what is the problem? For higher number of iterations, the learning rate may tend to 0. So if the learning rate tends to 0, nita into dou L by dou W, that will tend to 0. Okay. Okay, so in order to avoid this, so let me stop it over here. I hope your time is utilized perfectly, right? And you might have gone through, you can go through these things through the slides, okay? So, you please go through. But the big question is, how many inputs, how many layers, how many neurons in each layer, which activation function, which kernel initializer, which optimizer, what is the bed size, and what is the learning rate. And this can be done by using grid search, Bayesian optimization, or Schwarzschild evolutionary algorithms. Okay. Okay. Thank you.
Thank you, sir, for this wonderful session. Now, I would like to request Professor Mahendra Kumar Jena, sir, to present a token of gratitude to Professor Sibarama Panigrahi, sir. Now we will be moving forward with the next two sessions that will be conducted in virtual mode by Professor Parasar Mahanti from IIT Kanpur and Professor Viswaranjan Behra from ISI Kolkata. The virtual sessions will start from 5:30 p.m. All the participants are requested to join the meet link that will be shared in the WhatsApp group. I extend my gratitude to each and everyone for your patience and unwavering support in making this session successful. Thank you. Everyone is requested to head towards cafeteria for refreshment. And after refreshment, you have to go towards hostel, respective hostels. Thank you.
Please join after launch. Please, okay.
आईटी करे हॉस्टल पड़ेगा
हॉस्टेल बाहर कहीं बुली होनी है हॉस्टेल परमिशन आम देख पार ना